Dear students, welcome to the second online class of Control System Engineering. In first lecture, we studied about Introduction to Control System, what is control system, and course learning objectives. Then we studied about book to be followed and assessment plans. Then formally we start with the definition of a system, control system, and types of configuration. Any object that accepts input, process it, and give us an output is known as a system. And to obtain desired output from a system, we apply desired input. This is known as control system. And then we studied about controller, plant, and a sensor. Any system whose output is going to be controlled will be known as a plant. Its output will be measured by a sensor, and its output will be controlled with the help of a controller. Then we studied about configurations of control structure. First one is open loop system and second is closed loop system. The basic difference between open loop and closed loop is feedback path. In open loop systems, we don't have feedback path and have a predefined input-output relation. Where in closed loop system, we have a feedback path and we monitor the system's output with the help of an error. Then we studied few examples of open loop systems and closed loop systems. Then we made a comparison of open loop and closed loop systems, and after this we studied the course flow. If we are given a desired task, we'll start from mathematical modeling, transfer function, stability, time response specification, steady state error, and then control the design. After this, we studied test signals. And this was an overview of online lecture 1. Dear students, control theory is divided in two domains. If we are studying classical control, then we will be analyzing a system in frequency domain, and if we are studying modern control, then we will be analyzing a system in time domain. Our second chapter is titled as Modeling in Frequency Domain. In this chapter, you will study about Laplace transform, inverse Laplace, how to take Laplace transform of nth order differential equation, and to find out transfer function of the system. Then we will study various linear time invariant, electrical, translational mechanical, rotational mechanical, system with gears, and electromechanical system for their transfer function. Then we will study about analogous behavior of electrical and mechanical system, and we will get familiar with nonlinearities, and we'll study about linearization. Dear students, in lecture 2, we'll study about Laplace transform, definition, transform tables, transform theorems, how to find transfer function of nth order systems, and inverse Laplace. After Laplace transform, we'll study electrical network transfer function. In this, we'll find out transfer function of simple electrical circuits. Dear students, now starting with Laplace transform. As you studied in previous courses, Laplace transform of function f of t is an integral multiplied by exponential power e power minus st, where s is Laplace operator and is equal to sigma plus j omega. Graphically, S-plane is represented as a two-dimensional plane where one axis is sigma and another axis is j omega. For this integration, the function f of t must be integrable and must not be discontinuous at any time. Students, now we will study with the help of an example to find out Laplace transform of a function f of t, where f of t is equal to capital A exponential e power minus at u of t. This function is product of constant capital A, exponential function and a step function, which implies that for time less than 0, function results 0. Now to find Laplace transform, we'll use definition as studied in previous slide. Now using property of integration for exponential function, we come to result that Laplace transform of function f of t will be equal to capital F of s will be equals capital A divided by s plus small a. Now if we see time domain relation, the small a was present as a power of exponential term, where in Laplace domain relation this is present in denominator of the function. In last class, we have studied about various text signals which we are going to use throughout this course. And as we are studying frequency domain, so we will study Laplace transform of these text signals. These are the relations which we are going to use throughout this course for conversion between time domain and frequency domain. For delta or impulse, we have Laplace transform of 1, for step 1 over s, for ramp 1 over s square, and so on. Similarly, for parabola can be found with relation given in item number 4, and similarly Laplace transform can be found for sinusoid given in item number 6 and 7. Students, now we will study various theorems which will provide conversion of time domain to frequency domain relations. This table includes definition of conversion, linearity theorem, frequency shift theorem, time shift theorem, scaling theorem, theorem used to find Laplace transform of first order derivative, second order derivative, and nth order derivative. Among these three, it's important to note down that after conversion from time domain to frequency domain, initial conditions are also a part of frequency domain relation. Next is integration theorem, final value theorem, and initial value theorem. Now we'll study how to find transfer function of nth order system with the help of Laplace transform. For this, consider a linear time invariant system whose input is represented by r of t and output is represented by c of t. The nth order differential equation of this linear time invariant system is represented here. This equation also contains constants a naught to an and b naught to bm. Now for transfer function, we will take Laplace transform with the help of theorem studied in previous slide. And we'll come to an equation involving constants a naught to an, b naught to bm, Laplace operator s, and output represented by capital C of s, and input variable represented by capital R of s, and initial conditions associated with input R of t, and initial condition associated with output C of t. Further, we'll assume that all initial conditions are 0. This means that system is initially at rest, or we don't have any prior information of the system. After Laplace transform, our time domain equation is converted into simple algebraic equation, and after setting initial conditions equal to 0, we can simply take variable C of s common from all the terms involving it, and similarly R of s common from all the terms involving this. Now, using cross multiplication, we'll reach to desired transfer function C of s over R of s, which will be also represented by G of s. Okay, last we have a block representation of the transfer function. In previous slide, we were having a system with input R of t, output C of t. Now this is represented by, in Laplace domain as, a block diagram with input R of s, output C of s, and system is represented by transfer function G of s, whose numerator has highest power of m and denominator had highest power of n. So this is our transfer function for nth order linear time invariant system. Now to make things more clear, look at example. In this we have a first order input-output differential equation of a linear time invariant system, and we have to find transfer function. For this transfer function, first of all, we'll take Laplace domain transform with initial conditions equal to 0, which give us equation 2.56. Now this equation is simple algebraic equation where we can take variable common. You can take C of s common from terms involving SC of s and 2C of s. With this you will come up to s plus 2 whole multiplied by C of s, and equation will be equal to R of s. Now again using cross multiplication, you will reach to transfer function G of s, which is equal to C of s over R of s, and this will equal to 1 divided by s plus 2, and this will be transfer function of our linear time. Last topic under the series of Laplace transform is inverse Laplace. With the help of relationship given here, you will find out time domain function f of t from Laplace domain function f of s. But throughout this course, we will be using Laplace table and Laplace theorem studied in previous slides for conversion between time domain and frequency or Laplace domain. Now look at an example. In this example, we have a system g of s whose transfer function is given by 1 divided by s plus 2. The input applied to this system is step and is represented by variable r of t in time domain and capital R of s in Laplace domain. We have to find time response of this transfer function. For this, as we know that step input is represented by 1 over s in Laplace domain and output of the system is equal to input r of s multiplied by g of s in Laplace domain. Now for time response, we will check the relation of c of s may look familiar with any of relation from Laplace theorem table or Laplace input signal transform table. But unfortunately, we won't find any relevant form. So for this, we'll use partial fraction and convert relation of c of s into any appropriate form from that table. So after partial fraction, we have reached to equation half multiplied by 1 over s minus half multiplied by 1 over s plus 2. Now if you look at slide number 7, in which we have studied Laplace transform of various input signal, and these both terms get some familiar form. Now we will apply inverse Laplace on whole equation of c of s, and then with the help of linearity theorem, we will apply inverse Laplace on each individual term. Then using Laplace transform table for various signals, we will get time domain response c of t. And this is all about Laplace. Dear students, so far we have studied Laplace transform, which we will be using to find out transfer function of various systems. In the series of systems, we will start from electrical network transfer function. Under this topic, we will find out transfer function of various electrical network. And these networks include networks associated with resistor, capacitor, inductor, and we will also find transfer functions of operational amplifier circuits, which includes inverting amplifiers and non-inverting amplifiers. Before starting electrical networks associated with passive linear components, let us study what are these passive linear components. These components include capacitor, resistor, and inductor. If you look at the table, the first column specify voltage current relation for capacitor, resistor, and inductor. The second column specify current voltage relation for capacitor, resistor, inductor. The third column specify voltage charge relation for capacitor, resistor, inductor. The fourth column gave us impedance relation for capacitor, resistor, inductor in Laplace domain. And the last column gave us admittance, which is opposite of impedance for capacitor, resistor and inductor. In Laplace domain. Now we will start simple circuits for electrical network transfer function, which is an RLC network. If you look at the figure, in this we have inductor, resistor and capacitor connected in series, and source voltage is V of t and current moving through the circuit is I of t. And we have to find out transfer function relating capacitor voltage Vc of t to input voltage V of t in Laplace domain. The first step in finding out transfer function is to convert impedance of inductor, resistor and capacitor from time domain to Laplace domain using the table studied in previous slides. Similarly, the voltage source V of t and the current moving through the circuit will also be transformed in Laplace domain. Now you have studied a number of methods in the course of electric circuit analysis through which you can find transfer function Vc of s over V of s. We'll start from single loop differential equation method. For this method, we'll apply KVL at circuit. Now KVL will give us first equation, which states that sum of voltage across inductor, resistor and capacitor will be equal to the source voltage. Now we'll replace voltage across inductor, resistor and capacitor with its voltage current relation given in table at slide number 15. Now as we know that current is equal to the rate of change of charge, now replacing the current in the second equation will give us second order differential equation, and as we know that charge across capacitor is equal to capacitance of capacitor multiplied by voltage of capacitor. Now again substituting this, we'll have a second order equation whose variable are capacitor voltage and source voltage, where resistance, capacitance and inductance are constant. Now we'll take Laplace transform with zero initial conditions to find out transfer function. With Laplace transform, our time domain equation will be converted into simple algebraic equation. Now by simply taking Vc of s common and using cross multiplication, we can have our desired transfer function Vc of s over V of s. And we can analyze this system using a block diagram representation where input is V of s and output is Vc of s. Another method we can use is single loop transform method, in which we use Ohm's law, which implies that voltage will be equal to current with the product of impedance. Now from previous method we have applied KVL and reached to first order differential equation where variable terms are current and voltage. Now if we take Laplace transform with zero initial condition, we'll have a simple algebraic equation. Now using cross multiplication, we'll have a transfer function of current to source voltage. And on further simplification, we can have a relation for current I of s. Now using the voltage current relation studied earlier, we have that in Laplace domain, voltage across capacitor is product of current through the capacitor and impedance of capacitor, which is 1 over Cs. Now simply replacing the current and few rearrangement will give us our desired transfer function Vc of s over V of s, which is same as in previous case. Next method in this series is voltage division rule. With voltage division, we can simply find voltage across capacitor, which states that the component across which you are finding the voltage will be equal to impedance of that component divided by total impedance of the circuit, and this whole term will be multiplied by the source voltage. Now again, doing cross multiplication, you will get transfer function Vc of s over V of s. Dear students, the last method, single node through transform methods, through which we will find our desired transfer function Vc of s over V of s. For this, we assume that we have a node Vc of s. The current entering the node is equal to potential difference between the nodes divided by impedance, which is Vc of s minus V of s divided by impedance of resistor and inductor. Now current leaving through the node will be equal to Vc of s divided by impedance of capacitor, which is 1 over Cs. Now with the help of KCL, we'll obtain equation of the circuit, and then further solving with simple rearrangement, we'll obtain our desired transfer function. Now if any of you have any questions, please ask.